8.5, electromagnetism. We've already done some of it. The part we've already done is that a current, which is moving electric charges, can create a magnetic field. And that was an electromagnet. But then the flip side to that is that a moving or changing magnetic field can create a current. And if you like having electricity, then you love this principle, because it's pretty much how we make most of our electricity. Right. Now your book does the best job it can do trying to explain generators and motors and this interaction between charges and magnetic fields the best it can with just pictures and words. But honestly, I think animations or little videos help so much more. So let's just go through this with this little animation. So what I'm going to have here is basically a circuit without a battery in it. So I've got a coil of wire, and one end is hooked up to one end of a light bulb, and the other end of the wire is hooked up to another end of the light bulb. And there's no current right now because these little electrons in here are not moving. But if I move a magnet through the coil of wire, then the strength of the magnetic field inside that coil of wire is going to change. And that changing magnetic field pushes and pulls on those electrons and moves them. So I move the magnet back and forth through the coil of wire. It pushes and pulls on the electrons, which pushes and pulls them through the light bulb and gives us electricity. And if I add more loops, the effect would again be magnified, because there'd be more electrons in there to push and pull on. So I'm using here is a changing magnetic field inside the coil to make electricity. So now let's go to a generator. And here's a simple cartoon of a generator. Right, so right now we can see that there's a magnet, and around that magnet is a magnetic field. So just kind of a map of what the magnetic field would do. Let's hide this compass for now. Okay. But if I can get this magnet to spin a little bit, then the magnetic field will always be changing kind of direction and amount. And that changing magnetic field is also over by that coil of wire. And so that changing magnetic field in the coil of wire is pushing and pulling on those electrons, kind of back and forth, back and forth. So it's making alternating current, which can power a light bulb. Now, ideally, you would have the spinning magnet right inside the coil of wire because that would give you the strongest effect. But you could also, increase the number of loops. That would give you a stronger effect. Now, our United States electricity pulses at 60 hertz, 60 times a second. So that magnet is spinning much faster. So I turned up the water stream to try to get the magnet to spin faster. And so the magnetic field inside of that coil is now changing faster, which is going to give you stronger pushes and pulls. Now, an electric motor is basically this idea used in reverse. You would have a battery or a source of the electricity, and it would force the current through here. And as the current was forced through here, it would make its own magnetic field. Right? Electricity flowing in a loop makes its own magnetic field. which could then push and pull on another magnet, which could be attached to like the wheels of a car or something. So then the electromagnet can push and pull on the real magnet, or maybe an induced magnet, let's not worry about that now, and make the wheels spin or make the wheels stop. So a motor is just this idea in reverse. Now, almost all the ways that humans make electricity has to do with spinning a magnet. Windmills are obvious. The wind spins the windmill. Well, that spins the generator, which is basically spinning coils of wire, spinning a magnet. Turbines for dams of water, it goes through, spins a turbine, spins a magnet, gives us electricity. Yay! Nuclear power plants. Nuclear power plants use nuclear decay to boil water. And boil water is going to escape as high pressure steam, and that steam spins a turbine. And the turbine spins magnets and coils, and you get electricity. So we split the atom to spin a magnet. An exception to this would be solar panels. Right? Solar panels don't have any spinning magnets. They have a completely different way of generating electricity. Now, earlier I had given you this, where the amount of power is going to be equal to the amount of current times the voltage. All right, so let's talk about now why the power company likes to use alternating current to try to get us the electricity. So to move a certain amount of power, you can either use a large current or a large voltage. Right? So the power company has a choice. Now, large currents will heat the wires, and that loses energy as heat. That is not efficient. So you do not want to transmit the current to the customers. You want to transmit the voltage. So what we can do is use transformers, and transformers kind of convert between those two. So the power company might be making their electricity at 25,000 volts, and it would have some current. But it uses a transformer to boost the voltage, and that's also called a step-up transformer. It's stepping up the voltage. So it changes the voltage to be much, much, much larger. The benefit of that is that it reduces the current, right? And that also makes it much more efficient. But using, 100,000 volts or 300,000 volts isn't reasonable in a house, or even usually for commercial customers, so it's going to have to get stepped down again. So you can have another transformer to reduce the voltage, to step it down. And then, companies and factories might use it at something like 440 volts. But then it's going to get stepped down even more as it enters neighborhoods, down to 120 volts or 240 volts. And so when you do that, when you have those high voltage long distance lines running from the power plant to the cities, there's only maybe a 2% loss of power. It's very efficient. And remember, like a car is only 30% efficient, and an incandescent light bulb is only about 5% efficient. So once you reduce the voltage for safety, you will have less efficiency. You will have about 8% loss. So that's why they'll keep it as high voltage for as long as they can, and then step it down in voltage as close as they can to your house. All right, so how does a transformer work? So first, let's show a DC power supply. A DC power supply, imagine that this is your factory. This is your power generating factory. If it was making DC electricity and you were to run that through a coil, it would make a magnetic field, but it's a constant magnetic field. And that constant magnetic field doesn't really do anything over here to this other loop. And maybe imagine that this light bulb would be inside your house. So here the power company is using AC, and you can see that it's pushing and pulling the electrons. It's pushing and pulling the electrons, and that makes this magnetic field inside that loop switch back and then forth, and then fourth. And that magnetic field affects over here. It extends into this loop and it can push and pull on these electrons. So this is a pretty inefficient setup. Let me see if I can find a better animation that's more typical. Alright, so this is going to be what we call a step-down transformer, in that it is reducing the voltage. And that would increase the current. Anywho, so let's assume that this is from your high voltage lines. And the high voltage line would have a wire that comes in and wraps around an iron core. And then it goes back to the high voltage lines, kind of on a return wire. So this has to be AC electricity, kind of push and pull, push and pull. And inside of these loops of wire, then that's going to make a magnetic field. And this iron core amplifies that. So the magnetic field here will be north pole up and then north pole down. It'll flip-flop up and down. So the magnetic field in the iron is going to be flip-flopping every time this electricity flows back and then forth again. That magnetic field would reach over through the iron to through this other coil. So now you have a magnetic field that's flip-flopping inside of this blue coil. But now, since there are fewer loops on here, it will push and pull less strongly. So then over here you would have lower voltage. And the transformer only works because of the current is always changing. Push, then pull, push, then pull. If it was DC, like from a battery, the transformer wouldn't work at all. So not only is it easy to make AC by basically spinning a magnet in a coil of wire, but then it's easy to change the voltage, which makes it more efficient to get it to our house and then to change it back to lower voltage for safety.